to the first lecture of this lecture series on an introduction to molecular simulations. Introduction to molecular simulations. So in this course, we are going to be covering a lot of important topics related to molecular simulations and their implementation and the physics that is required to understand how they work and how to code them numerically. So to start the class, I want to give a quick introduction to modeling. So, and this is sort of a broad overview of the different types of models that we will use to do molecular modeling. So in general, when we think of modeling, we need to think about what length scale and what time scale is accessible to the system, or of the system that we want to model, and what is accessible to the model we're using. So it's good to draw this sort of graph here, where you have your time scales and your length scales. Now, there's sort of two general approaches to modeling. There's what we call a bottom-up approach, which starts here in this corner of the diagram and goes this way. And there's also a top-down approach, top-down, which starts up in this corner and moves that way. And depending on the problem that you're interested in, you may need to start from either direction. But just as a brief overview, we're going to start by looking at a top-down approach. So what are sort of the biggest time scales and length scales that we have access to within physics with respect to these molecular simulations? Well, the first one is macroscopic or continuum models. Continuum models. So these are going to be like your thermodynamic models, your fluid mechanics models, and things like this. Of course, you can get smaller length and time scales with these guys, but just from what you're mostly familiar with from your undergraduate level classes in classical thermo and classical fluid mechanics, these kind of live in this first part of the diagram here. The next branch down is what we call mesoscale models. Mesoscale. Mesoscale models are not quite a continuum model, they're not quite a molecular model, they're somewhere in between. So a really good example are things like nano or microfluidics. Micro and nanofluidics. Nanofluidics. So the flow of fluids in confinement, when you have essentially a small enough length scale that you can no longer rely on these continuum models anymore, you need some statistical mechanics or to keep track of the behavior of the particles. An example of a type of algorithm within molecular simulations that is considered a mesoscale model is dissipative particle dynamics, or DPD. Dissipative particle dynamics. DPD. Now we're going to get into what we traditionally think of as a molecular simulation. And the first, sort of in this top-down scheme, are the coarse-grained models. Coarse-grained models. Coarse-grained models are molecular models in which we don't actually keep track of all the atomic information in the system. So you can imagine, right, if you were to model a water molecule as an oxygen bound to two hydrogens, this is what we would call an atomistic picture. Atomistic. In a coarse-grained model, you might say, okay, I don't want to deal with these hydrogens. Instead, I'm going to treat this water molecule as just one sphere with specific interactions. So you're sort of, you're losing information in the sense of the atomic coordinates, but you can actually do a really good job at modeling systems by reducing the number of coordinates. And what this allows you to do is it allows you to gain access to longer time scales and longer length scales than the most traditional approach to molecular mechanics, which is the atomistic simulation. Atomistic. These are going to keep track of every atom in the system and how they interact with all other atoms in the system. And of course, because there's more coordinates here, the computation is going to be more expensive. So that's why we have a lower length and time scale. Now, the sort of last group of methods that will not be deeply covered in this class are quantum mechanical methods. And I don't have much room here, but they live right here. So these quantum mechanical methods are extremely powerful for determining specific types of electronic structure interactions, or if you have light atoms like hydrogen in your system, you can use quantum methods like path integral molecular dynamics to keep track of the motions and distributions of the light nuclei, of the hydrogen nuclei. But in this class, we are not going to cover quantum mechanics in detail. This is a whole other subject. What we are going to focus on are these two here, atomistic and coarse-grained simulations. And this, for the sake of this class, this is what I'm referring to as a molecular simulation. These are molecular simulations. So what are molecular simulations? Well, molecular simulations are computer programs that keep track of the positions, energies, momenta, and dynamics, or time evolution of these things, of a system of atoms. A system of atoms. So, in general, molecular simulations are going to be a way or a model for how these atoms are actually moving around. And we're going to need to keep track of some really important quantities related to that motion. Of course, we have the positions. The momenta are extremely important with respect to what we'll talk about later in Hamiltonian mechanics. And then, of course, looking at the energy of the system. We know that things like free energy will be minimized in closed systems. So we need to keep track of these types of quantities in order to understand the system better. And then, of course, if we can keep track of these quantities in time, we can actually watch the dynamics of the system, or how particles evolve in time if we're using molecular dynamics. So to understand and study these systems, we really need three primary branches of physics, or three sort of different branches of physics to come together, and actually I would say maybe a fourth as well. So we need three branches of physics here. Physics. and you can be pedantic about what a branch of physics is, but I'm breaking these up in this way. So the first one is classical mechanics. And specifically, we are going to use, of course, we're going to use Newton's equation of motion. The force is equal to the mass times the acceleration. But really what we're going to need in classical mechanics is what's known as the Hamiltonian formulation, or Hamiltonian mechanics. And later in the class, we're going to get into what Hamiltonian mechanics is. But it's essentially just a reformulation of classical mechanics in terms of different variables than classical mechanics, or than traditional classical mechanics that you might have learned in a undergraduate physics course. The second important branch is classical thermodynamics. This is your conservation of energy, your first and second laws. Classical thermodynamics. So this is going to be really important when we're talking about the behavior of the system. For instance, if we are running a molecular simulation and our simulation isn't obeying the rules of classical thermodynamics, then we know that there should be something wrong, at least if we're modeling something like a bulk system. So classical thermodynamics is going to be extremely important to have a good intuition for and a good understanding of when we're approaching these molecular simulation models. The final one is statistical mechanics. Statistical mechanics is a field of physics in which we study large numbers of things in a statistical sense. So rather than keeping track of every particle using F equals ma, or looking at the system from a macroscopic perspective with classical thermodynamics, statistical mechanics is going to give us the tools to actually keep track of a lot of particles at once and their collective behaviors, looking at things like statistical averages, expectations, and this is actually going to give us the main results that we need to understand and implement molecular simulations. This is an extremely important field, and a lot of this class is dedicated to working towards giving you a good introduction to statistical mechanics at a level that is high enough that when you encounter something like a molecular simulation in literature, or you're thinking about molecular simulations in general, that you actually understand how how these systems behave on average. The last thing that we're going to need, and we're only going to need this peripherally within statistical mechanics, is we're going to need quantum mechanics. And we're only going to need this in a couple places for our purposes, but of course, like I said, this is a whole field on its own, and you can approach the study and modeling of systems using quantum mechanics directly, if that's appropriate for the system that you're interested in. So what questions can, I'm going to say, molesims help answer? Well, one of the most important and sort of one of the main drivers for the development of molecular dynamics was to study the structure and energetics of atomic systems. Recall from your organic chemistry how, for instance, in something like cyclohexane, you may have different conformers of the molecule that could have these different configurations potentially. And you might ask, okay, well, which one's higher energy? Which one's more likely to be, which structure is this molecule more likely to be found in? And you learned some general rules inorganic chemistry about this. So you'd say, okay, well, this is more likely. This is a more low energy structure. But what if you had a lot of these interacting all at once? It's not super trivial to just choose, which structure or which atomic system makes the most sense. But molecular simulations are going to help us keep track of those types of realizations of the structure and the energetics to let us make decisions about what seems more likely or what is more probable. We can look at things like biomolecule folding, so proteins, for instance. If we start with a protein in a simulation box and it has some water, it's contained in an aqueous environment, how does it fold? Does it go through some interesting hairpin and form some sort of helical structure and curl around? How long does this take? What path does it take to get to this folded state? These are all different types of questions we can answer about structure. So we can have, just write this, we can study conformations. We can study protein folding. And the last example I have here is we can actually study things like nanoparticle aggregation. Nanoparticle aggregation. For instance, if you have some nanoparticle in a bath of different polymers, how do these polymers go and interact with the surface? What types of structures do they form? Do they land on the surface and coat it and lay flat and make some sort of weird absorbed layer here? Do they instead form hair-like particles that extend off? What is the lowest energy state of the system? So you can see there's a lot of examples of where we would care about these sorts of things, whether it's trying to understand the behavior of a chemical process in chemical engineering, in industrial process engineering, whether it's understanding how a protein folds so we can build a new pharmaceutical, or looking at how nanoparticles aggregate if we're designing some special system to keep track or do nano sensing from these polymeric hairs sticking off and interacting with something in the solution. So you can imagine there's a lot of examples of when molecular simulations are going to be extremely important to helping us understand how atoms and molecules structure themselves and how they're most likely to structure themselves. So the second sort of class here, or the second sort of question we can answer is, now rather than just looking at the structure and energetics, we can actually look at the dynamics of the system. This is if we're using a specific type of method called molecular dynamics. And we're going to get into the distinction a bit later, but I just want to give this broad overview to sort of motivate the problem. But the second sort of question we can look at is dynamics and kinetics. And in layman's terms, this is essentially how fast do things happen and how do they happen in time. So specifically, we can ask, how do structures evolve in time? How do structures evolve in time? The protein example is perfect for this. Evolve in time. What paths do they take? How do structures evolve in time? We can also study things like transition states and look at non-equilibrium things where you actually have, potentially some state of the system like state 1, and it is transitioning, or we know it transitions to some other state, but there's a lot of different paths it could take to get there. And a big question is, what path is it most likely to take? So this is a sort of problem in non-equilibrium statistical mechanics that we can actually use simulations to investigate. And this is a very recently explored field in non-equilibrium statistical mechanics. There's a lot of really cool physics that can be done with this. You can also ask, at what rate do structures form? At what rate do structures form? Do structures form? So with respect to the research in my group, in the Hefner group at the University of Utah, we care a lot about the aggregation of asphaltene molecules. So asphaltenes are these really complex organic molecules that are found in crude oil, and they can cause a lot of problems related to oil production and treatment. And one of the things they do is they form these really nasty aggregates that can cause fouling in pipes. Now, one thing that's really interesting is no one really knows how these asphaltenes aggregate, like what the mechanism is. So something like molecular simulations could help us investigate that. But also, you need to know how fast these nanoparticles form, or these nanoaggregates are forming, and how they're growing in time. And we can actually use molecular simulations to investigate that sort of phenomena. We can also look at things like how fast does it, or how long does it take ice to melt? You have something like ice and it's at a higher temperature, well, it's going to go to a liquid. How long does that take? Another good example is if I have a protein and I increase the temperature, how long does it take for it to denature? These are all different types of questions that we can investigate with respect to the dynamics of molecular systems. Third category is that we can study things like thermodynamics or thermodynamic properties. Thermodynamics. We can look at properties like heat capacity, entropy, isothermal compressibility, and another example I'm very fond of, vapor-liquid equilibrium, or phase equilibrium. Crystal formation, and the list goes on, etc. We can investigate a lot of very interesting thermodynamic properties using molecular simulations. We can also look at model systems, so we can investigate models thermodynamically, like models that are common that we care about are hard particle models, hard particles, Leonard-Jones fluids, me fluids. We can really investigate the properties of these systems and understand from a very fundamental perspective how these systems are going to behave, and then compare those to real life situations and try to see where do the models need to be improved and how do we need to adjust in order to actually model reality in an effective way. So these are sort of the main three categories that we will explore. And of course, there's many more that could be thought of, so don't judge me too hard for not writing them all down. But this is just to give you a broad overview of what molecular simulations can do for us and what types of systems they let us study. The next thing I want to talk about is how do molecular simulations work in general? How do molecular simulations work? Well, there's of course many different methods to run molecular simulations, and there's many different ways of getting to the same answer, and we're going to discuss these in the class. But really in this part, what I want to make an important note of is that in principle, if we were to model this perfectly, atoms are quantum mechanical. So we're just building models here. We know that this is a more precise theory of how atoms behave, but we're not actually going to invoke quantum mechanics. What we're going to do is make some important assumptions to simplify the modeling process and enable us to actually perform these calculations on a large enough scale to study complex systems. So we're going to make two important assumptions. The first one is that the motion of nuclei, or of the atomic nuclei, behave classically according to Newton's equation of motion. So we're going to be able to use F equals ma to keep track of the positions and the momenta of the particles. Now, when would this be violated? Well, there's a few instances, but one example is if you have things like hydrogens in your system, they will actually behave quantum mechanically, and we will need to keep track of that for certain applications. And when this is violated, so just as a brief, so a violation of assumption 1 will happen in light atoms and or low temperatures. And our pivot, or what we're going to do instead here, rather than classical molecular simulations, we're going to do path integral methods. Path integrals are going to give us a way to keep track of the quantum mechanical nature of these atoms. But we're not going to deal with those. The second major assumption is that the interactions between atoms can be modeled by a classical potential energy function. Potential energy function that is what we call pairwise additive. Pairwise additive. So what does pairwise additive mean? We have our system. Let's say it's of n particles. Our potential energy is a function of the positions of all of these particles. We'll write that like this. And really what it is it's a sum of contributions of many different types. So we'll have contributions, if we have some external field force here, we'll have contributions on each particle by this force. So we'll have contributions to the energy from there, and we'll call this U1. and it's a function only of where the particles are. Something like that. Here's your external field contribution. External field. You'll have now a double sum related to contributions from pairs of atoms. So you're going to have I equal 1 between j not equal to I from n to n of a potential energy function that depends on the relative positions of two atoms at once. Something like this, right? And that'll have some different functional form than f. This is the pair term. And then we can just keep going. We have triplet terms. So I equal 1, j not equal I, k not equal j. From n to n to n of a triplet term, so something that depends on the relative positions of three particles at once. And this spans the entire set of particles. This is going to go on until we hit n sums here, where n is the total number of atoms in the system. Now what the pairwise additive assumption is, so the pairwise additive assumption is that what we can do is we can take all of these higher order terms, all of these extra terms, and we can actually collapse them down into this term, into a pairwise term. Now, of course, this is an approximation because we're losing information about these many body interactions, but what we're gaining is computational simplicity. So this is going to speed up our algorithms, and it's going to make a lot of these calculations possible. In certain instances, you may want to include these terms, but for now, we're making this pairwise additive assumption that all of these can get lumped into this term. And when we do this, typically we call this potential energy, this pair term, an effective pair term. So this becomes the effective pair term, or the effective pair interaction. And often we don't have an external field, so a lot of the time this is just not in our simulations at all. It can be in certain applications, but for a lot of the time we're only dealing with this sort of pair interaction. So what exactly is this pair interaction? Well, in general in our system we can keep track of every particle at once, right? We can keep track of particle 1, particle 2, particle 3, and so on. The pair term is going to look at the relative positions of two particles at once. So let's say particle 2 and particle 3. Where's particle 2? Where's particle 3? And that's just going to give us a number, some scalar, which is going to describe the potential energy of these two particles together. And what we're going to do is add that up over all the possible combinations of pairs in the system. So this is generally how we're going to calculate the potential energy of the system. And generally as well, this is going to be able to speed up our calculations a lot because we're ignoring these more complex terms. Or let's look at an example of a potential energy function. So the classic example, the one kind of most everyone starts with, is called the Leonard-Jones potential. Leonard-Jones potential. Its equation is U of r, and here the r is equal to the relative distance between two particles, is equal to 4 times a parameter called epsilon. This is the dispersion energy. Times this interesting set of terms here, this sigma over r to the 12th term minus a sigma over r to the 6th term, where sigma is what's known as the collision diameter. You can think of it as a size of your atom. R is going to be the relative distance between atoms I and J. This power 6 here is going to come from the classical solution for an induced dipole-dipole interaction. And this 12 is actually just going to be chosen for mathematical convenience because it's the square of the power 6 term. So once we've calculated this guy, we can just square it to get the other term. Now, what does this function look like? And what does it mean? Well, first let's think about these two atoms, I and J. They have some vector pointing to them from this arbitrarily chosen origin. Ri, Rj. And the distance between these two is going to be here, R. So we kind of can see what we're doing here. When we calculate the potential energy of particles I and J using this formula, what we're doing, this will actually be easier to plot here, is we're just plugging this R into this equation with a given set of epsilon and sigma parameters, and that's going to give us the potential energy between these atoms. The way this function looks is it has an extremely steep short range, a potential energy well, and then a tail that tails to 0 out here. Now your sigma parameter is actually going to describe where this potential crosses the x-axis. So this here is sigma. This well depth here is going to be equal to minus epsilon. This is the depth of your potential energy well. So when you think of a potential energy function, right, I think the easiest way to think about them is by looking at what forces come out of it. So in general, the force with respect to a potential energy function is equal to the minus gradient of the potential energy. So the minus derivative, the negative derivative. Well, let's think about what that would look like for this plot. So here, at the short range, the derivative of this curve is negative. And then we need to take the negative of that so it's positive, right? So there's going to be some positive contribution here. And this curve is going to be negative all the way down until we hit this point where the derivative is going to change sign, because it's 0 here. There's a minima here. So it's going to be positive. This is the force. Function of R. It's going to be positive until we hit this point. Then we have a positive derivative, but we have to take the negative sign. So now we're going to go negative. We're going to come down here, and then the magnitude's going to start shrinking until we go to 0. So what does that mean? What does it mean when the force here is positive, the force here is negative? What does it mean when the force is positive? Well, you can think, right? This is R along this axis here, and this is U of R, right? What you can think of is if R is really small, these atoms are really close together. In fact, if they're over here, they're essentially overlapping. Well, we know from the Pauli exclusion principle that the electrons in these atoms do not want to interact with each other. They cannot interact with each other physically, and so they're going to cause something called Pauli repulsion. This repulsion is going to want the atoms to move apart from each other. Well, within the reference frame we've created here, that is what a positive force is. The positive force wants to push the atoms apart. So when they're close by, there's a really high force that's wanting to move the atoms away from each other. Now, once you hit this change in sign here, you reach, so you can imagine now the atoms are starting to move away. You reach a point where there is no force. This is sort of where the atoms like to be, or where they are going to enjoy hanging out, right in this potential energy well. So at this point, at this inflection, the atoms don't feel anything. There is no net force. But if we keep going past this point, now they're going to experience a negative force. A negative force within our reference frame means that the atoms want to actually come together. And what you can see is in the limiting behavior, as these get really infinitely far apart from each other, it's going to tail to zero because it's as if the particles don't even know that they're there. So this sort of potential energy function makes sense. It makes sense with our intuition. We can't just arbitrarily let atoms overlap because of the Pauli exclusion principle. At some point, the atoms are going to want to attract to each other due to dispersion energies. And once you go really far away, the atoms aren't going to feel each other anymore. So this is a really classic potential known as the Leonard-Jones potential. And pretty much all of the pairwise additive systems that we're going to study are going to have potential energy functions that take this type of form. All right, so let's do a quick overview of what I'm introducing now, a molecular dynamics simulation. Overview of a molecular dynamics simulation. How do these things generally work? Well, the point of this class is going to be actually to get you to coding these things from scratch, and not necessarily for research applications, but for your own understanding. And then once you've gained that understanding, we will move into using existing packages like LAMPS and Hundi, which we use really widely in our research and is also used worldwide. So, sort of the first step is generically is building a system. Build the system. This is actually a pretty non-trivial step. You need to create a system of particles. You need to populate some computer simulation box with those particles. Maybe I'm interested in this polymer, or maybe it's a protein, and I'm interested in how it folds in a solvent, or in let's say in water. So depending on how I'm modeling this water, I'm going to need to populate the box with little water molecules. This polymer here, this protein, and I'm going to have to do it in a way where the system, where it makes sense and the system won't actually have too high of energy and not be able to be calculated. So that can be tricky, and there's a lot of packages that can help us with that. The second step is we need to choose our potential energy functions. Choose potential energy functions. So in this example, we need to know we need a potential energy between the particles in water, how they interact with the protein. We need a potential energy function for how the protein interacts with itself. Maybe even how the water interacts with itself. And these are very generic. We need to know how, depending on the simulation, we need to know how the bonds in the protein work, the bonds in the water work, how the non-bonded terms work, how the particles are going to twist and bend. So there's a lot that goes into defining these potential energy functions. The third step is going to be initializing the system and then solving numerically the equations of motion. So this is why it's molecular dynamics, because we're actually solving the Newton equation of motion here for this many particle system. And then from that, we need to invoke statistical mechanics I'm going to write StatMech to analyze how the particles move, to analyze the trajectory is what we'll call it, trajectory. The trajectory is how the particles are moving around in space. You can think of the trajectory as like a movie of how these particles are moving around. And from that, sort of the last step is that we learn about the system. We make judgments about the system, we determine what's going on. Maybe we try to answer our original questions that we had for why we even set up this simulation in the first place. So the main goal of this class is going to be to go through each of these types of steps from a very fundamental place. So starting with the physics and then building into using numerics to actually do these things on your home computer. And practically, you could just go grab a package off the shelf and go through the documentation and do their overview and whatever. But this class is really going to focus on how do you actually code this stuff from scratch. So how do you start from this basic physics and go through the journey that researchers have been going through to get to where we are today. And in my opinion, going through that exercise once, especially at this sort of advanced undergraduate level, will give you the tools you need to understand how these packages work. So thank you for listening to this video. This is the overview of molecular simulations and sort of the start of the class. So hopefully you guys are excited to dive into the physics. The next lecture will be on an introduction to classical mechanics and specifically getting at definitions of kinetic energy, potential energy, and deriving the conservation of energy by only using the definition of work and the Newton equation of motion. So thank you very much.